All right. So first thing I want to do is I want to not really revisit, but I want to visit with you an area that I'm not going to say you've seen it before, but you've kind of used the skills. But I just kind of want to refine them and make sure that you guys would interpret this type of problem correctly. Actually, have some things up here that are in color. You probably are still going to want to jot some of this down. But if I gave you a space like this, if I gave you an area. It's supposed to be represented by sort of that yellowish area there. So if you were trying to find that yellowish area, which is kind of like snuggled above the sine wave. So we've got a sine wave if you're going to draw yourself a little sketch. All right, there would be some things that we'd want to start to observe, especially now that we've kind of been around this a little bit. I just want to talk to you about them though, instead of me saying, here, try it. Let's kind of talk it through, because there's some things I want you to see. One of those things is that the boundary for this like yellowish region is actually a y value. Now, how would you know that that's y equals 1? The graph, would be drawn to scale and such. But just notice that the boundary to that region is a y value. Here's the funny thing, though. You're not going to use that. I want to say to you again, I think I've said it at least once, but this is like something you really want to process today. You never use y values when you're doing a dx integration. Do you know what I mean by that? Every time we do an integration with one of those integral signs, it's always from x equals a to x equals b. So the funny thing is we've got a y value, we notice it, but it's not going to sort of be in our integration. Instead, it's the x values. Now, can you see here I drew two like green dashed lines? It's the x values. And it almost seems like they're not, it's not right, but it is, because it's the x values that always create our limits of integration. Okay, so I guess what I'm really saying is that is what should catch your attention. It's the x values that should catch your attention in this somewhat strange diagram. All right, so it's the area, or I should say the area that is under the curve, and you've seen this now a few times, and you guys are doing really good with this, but the area that's under, oh, we got rid of the y value. The area that's under the curve is the integral. And I'm kind of at the spot where I would say, I'm imagining that you guys realize that you're going to do some integral of the sine of x. Yes, you're going to do the integral of the sine of x, but you want to realize that that is that purple region. And again, you guys are doing a nice job with that, which is great. That's a big part of this chapter. All right, do you like my color coordinating here? So we've got this sort of this purplish color, which is the integral. And then it's really this rectangle. I just kind of have it shown as a rectangle, but it's this rectangle. And have you kind of seen the rectangle? It's the rectangle that basically represents all of the area. And that rectangle is a 1 by pi over 2. 1 by pi over 2 are the two dimensions of that whole rectangle. I encourage you to do something to see if you can get an answer here. I don't want to just click, click, click and show you stuff. Can you take what we've done here? You might feel like you've done something like this a few times, but can you get the correct final answer for this? If you're doing the problem with the antiderivative, make sure that you get that opposite cosine for your antiderivative. Okay, so if you subtract these numbers carefully, be careful about this. I know I've said it a time or two before, but you get lots of ones and zeros and negative ones, but we want to subtract them carefully and maybe not be surprised that the answer comes out to be 1. Just saying, the whole area under the sine wave we talked about a few weeks ago as being 2. So here we see that half the area, the purple region is half that area, comes out to be 1. Okay, and then again, your rectangle area it's a 1 by pi over 2. Make sure you realize that 1 is the y dimension. It's interesting, you do use the number 1 as your y dimension here. And of course, pi over 2 is your x dimension. So we have ourselves the classic subtraction problem where you're going to subtract your big area minus your small area. It's basically the green minus the purple is going to equal the yellow. So we end up with our yellow area, which is really what we seek, to be pi over 2 minus 1. You can actually leave the answer like that. That's fine. It's pretty appropriate. You could also turn it into a decimal, which, what is that? Like 0.57. Is there something that happened here that you have a question on? Are you tracking with me about how we kind of look at the x values? You see a rectangle, and ultimately you subtract the big minus the small. I haven't actually done much with this. That's a little bit on purpose because I want to make sure you guys are learning sort of the I'll call it the real math. But there is a function on your calculator. It's called f(n)i(n)t. And yeah, I want you to know what it does. f(n)i(n)t is able to do an integral. That is an integral that comes out to be a number. So if I want to do the integral of the sine of x from 0 to pi over 2, remember some of your calculators, when you type this type of thing in, it shows the integral symbol. My calculator, I have to use commas, but it's going to do the integral. Notice that I don't have to figure out the antiderivative to be opposite cosine. Okay, but it kind of does that work for you. Are you allowed to use that? If you understand what it's doing. Now, there will be questions where I say you must show the antiderivative. You must show opposite cosine, but you could still check your answer using f(n)i(n)t. Okay, you'll see some problems where the area is in a different space, like you've seen before. What I'd like to do now is, and this will be our other thing that we do here today before I give you the exit question, I want to talk to you about an application of average y value. We call it average inventory, but this is an application of that average idea. Bless you. If you're able to look at your book, this will be a little more worthwhile. If you can't look at a book, I would pay some good attention, or maybe grab a quick picture of somebody's if you can. Page 285. You've heard me say this before, and it doesn't hurt to say it again. There's a whole business side to calculus. In other words, every application has something to do with profits and marginals, and in this case, inventory. Okay, as I've told you before, I'm not an expert on these things, but I think we can understand this because simply, even if you look in the book or if you look up at the screen, we have an I equation, which is an inventory equation. And basically what it's saying is that I can integrate that equation. Now, this is one of those things that I didn't quite understand when I was a student, but that doesn't mean you can't understand it. When you do an integral of a function, yes, you find the area under it, but you're going to learn that what you also find is like the total amount under it. You find like the total amount of distance traveled, or in this case, we find the total amount of inventory, of basically stuff in the warehouse. And if you read the problem in the book here, it's example 9, it says that there's some type of wholesaler, basically, they're selling, in this case, chocolates, and 1,200 cases of chocolates show up every 30 days. So basically a truck arrives and they put 1,200 boxes in the warehouse. And then, as it says, each day, and this is kind of a simple example, but each day, so many of those chocolates are shipped out. If you look at the equation, it says 1,200 minus 40x. Well, I think that means that 40 boxes are shipped out every day. Okay, now you could approach this problem from just kind of a common sense approach. If 1,200 boxes are in the warehouse and every day 40 of them disappear, okay, what's our average going to be? Okay, the nice thing about this problem is that it's kind of a steady decline. But the purpose here is to realize that we can use calculus to also find that average. And I'm kind of using the problem out of the book there, but I think I have, so, I of X is the total inventory, and then we'll be able to use that to find this average inventory. Let's do that. Let's do the problem. They actually did the problem in the book. You can just look at it in the book, or you can still jot it down because, and this is the part that a couple of you forgot on the assignments. Make sure that you realize that it's part of the average formula. That is that you always have to divide by the total number, in this case, the total number of days. You're basically dividing by the interval, the length of your interval. We're going to also integrate our I equation, which is 1,200 minus 40x dx. Now I'm going to, just for something different, I'm going to use f and I and t again. Okay, I'm going to use f and I and t to find that integral. You could use the antiderivative. It does make quick work of calculating the area under that graph. It's an interesting number. I actually kind of want you to look at that with me and realize that it means something. Yes, it's the area under the graph. But when it gets divided by the total number of days, we end up with the average amount that's in the warehouse. It's kind of like the amount that would be there on that 15th day, on that middle day. So what exactly is 18,000? Because it's not the total number of boxes in there. What exactly is 18,000? I don't know. I'm kind of asking that question, honestly, even of myself here to try to process what that would be, besides just saying it's the area under the inventory. Let me sit on that a little bit. I feel like I lost it, skipped my mind how we can describe what that 18,000 is, rather than just saying it's the area. All right, there's another part to these problems. Usually it has to do with money. It has to do with money, and it's just a simple concept because basically it costs so much money to keep stuff in the warehouse. So in this case, the average inventory times that holding cost. Okay, if I know what my average is, but I know what my holding cost, H is the holding cost, then I can come up with that average amount of money. If you read the problem a little bit out of the book, it tells you that the holding cost is 3 cents. So we can do some common sense thinking, which is what this formula really says, okay? Because your average cost is obviously going to be 3 cents for every one of those boxes. So I can take 3 cents times 600. Okay, and that's how they came up with $18. Now that's $18 a day. Although in the beginning of the month, it's going to cost more, and at the end of the month, it's going to cost less, but that's your average, which matches up with your average of 600. I'm kind of bugged by that 18,000 number. I don't know if it's really bugging you or not, but I want to think about that a little bit more. What does that really represent? Okay, in your assignment, you'll see a couple average inventory questions. It's just the average Y value kind of resurrected in a simple application. All right. Well, okay. This exit question is a little bit more of a, honestly, a little bit more of a sample of some test questions. It's a good sample of putting all the ideas together